Well, hello everyone. Welcome to this afternoon's session. I'm AJ Frazer, Vice President of Business Development for Agent VI. And today we're going to be talking about common misunderstandings or mistakes that are done when designing new analytics systems that use AI. And so for this session, it's going to be a quick session, about 30 minutes. We're going to go through a lot of content. We're going to try to squeeze in a quick demonstration of some actual cameras. And at the same time, hopefully we'll leave a little bit of time at the end for questions. 30 minutes doesn't go far, so let's see how far we can get here. So to begin with, if we really want to have a discussion about designing for AI, I want to give you just a little bit of background on Agent VI. This is the only slide I have in the presentation specifically about Agent VI. But we were founded in 2003 with a patent that was designed around the idea of how to break up an analytics pipeline to more efficiently use hardware. In 2003, video analytics was a pretty new thing, and it was actually very hard to run analytics on any of the current hardware at that time. So after our founding, we launched a product. We were very successful with it, and over our first 10 years, we built a global business with over 5,000 deployments in 90 different countries, primarily based around real-time detection, search, and business intelligence. So, and that was a good product for us. And it took us, through 2013, but by 2014, we began realizing that we were starting to hit some of the limitations of just what we could do with that current technology. And at that time, we began experimenting with what then was called deep learning, what a lot of us now call AI, but really it's based on a concept of data extraction called deep learning. And so we did some pilots and concluded that this was really the way of the future. And in 2016, we launched a completely new product line from ground up, an AI-based platform. We launched it as a cloud service, and then shortly after that began offering it also as an on-prem offering. That new product is called Anomaly. That was a great product. The performance was excellent, but we learned a lot about how to deploy and manage these type AI systems. And by June of last year, 2020, almost a year ago, we launched a second generation of our AI platform. Now we have over 1,000 sites running on the Anomaly AI analytics. And in fact, all of those customers, or almost all of the customers that were cloud-based since 2016, not only got regular updates, but most all of them have updated to the newer version of Anomaly. Only a few have not, but I expect actually those few will probably update here soon. So this has been a very good platform for us. But as I said, we've learned a lot about how the analytics work and also about the way people think and understand analytics. So let's start by talking a little bit about what is the difference with AI analytics versus the traditional analytics. And so to get into this discussion, I'm going to explain a little bit of the way analytics used to work. And by the way, as a full disclaimer, there's still a lot of companies out there around the world offering video analytics using the traditional, what we call the traditional VCA algorithm. And what traditional VCA algorithms did is they would look at video and they would look at groups of pixels, and those pixels would basically be then characterized. What's the aspect ratio? How large are they? How quickly are they moving? Is it a small group or a big group? It's what I would call blob analytics. And with the blob analytics, we were able to do a lot. And 20 years ago, that was pretty groundbreaking. But they had a lot of limitations too. So by comparison, to contrast with that, deep learning or AI algorithms, they see and understand what the detected entity is. So if you're trying to detect person, they're looking at that video image and they're looking for something that actually looks like a person. The more it sees, the smarter it gets. And the best way to try to explain this with an analogy, it's actually the way the human brain works. Now, those who know me well know that I have 3 daughters. And my oldest daughter is now 27, and I have a 24-year-old daughter. And when they were young, we would give them food, and it didn't take very long before, if we came into the kitchen with a bowl of ice cream, after a couple times of doing that, they began to recognize, ooh, that bowl of ice cream looks really good. And then maybe we would give them some fruit. So we might give them bananas, and we'd say, this is a banana. And then we could give them an apple, and we say, this is an apple. Now, it didn't take very long before my daughters realized that a bowl of ice cream and a banana and an apple do not look like broccoli. Okay, so through positive identification, even though they might not know what broccoli is, they knew it was not a bowl of ice cream, for example, in priority. So that's an example of positive identification. Well, what we do with deep learning is something similar to that. We write an algorithm that, by feeding it correct images of what it is we're trying to classify, the algorithm learns what that actual object is that we're trying to classify. So, for example, when we launched our first version of Anomaly, our first AI, it had about 30,000 reference images that were used to train it. What does a person look like, and what does a vehicle look like? And that's pretty much all it did. It could do a person, it could do a vehicle. And I just got to say, even in 2016, even with that limited classification, the results were phenomenal. It ran well. The classification was good, and that's part of the advantages that you get with an AI algorithm. You're able to achieve much more precise object classification. So, for example, at this point now, we've introduced into our learning set over 1 million different images. So we can not just tell the difference between a person or a vehicle, we can also tell the difference between bicycles, motorcycles, buses, trucks. We can even teach it new classes of objects by just feeding it valid reference images. And this has another benefit to it. This improved classification also comes without any manual configuration, testing, or tweaking, as we used to have to do with what I'll call the VCA blob analytics. So if you look at these two real examples from our system, you can see that image on the left with our traditional analytics and the way analytics were traditionally done in the market. With that much motion in the scene, there would have been no chance of detecting that person, because, as I said, the VCA depended on motion to then group pixels to then try to decide what is the outline of this thing that we're trying to detect. But with the newer AI algorithms, it doesn't work the same way. It actually can identify, even through the steam there, that there's a person in that image. Another problem the traditional analytics had was if there was any kind of obstructions on the camera lens, like bugs or raindrops in the case of the picture on the right. Well, with the new AI algorithms, once again, they're less bothered by that kind of bad video, because they can still see through the obstruction to see that there's a person or something that looks like a person moving through that field of view. So very good classification, without manual configuration and with low false alarm rates. Now, let me say something about the false alarm rates. This is actually not magic. It's sort of inherent in the way these new deep learning algorithms work. So let me go back and abuse my analogy just a little bit with my daughters. So, as I said, I would teach them what ice cream looked like. Well, at that point, if we put broccoli on their plate, they had no interest on broccoli, because they had already been trained ice cream was what they wanted. So, in a way, the nuisance filter for my young daughters was they had broccoli was a nuisance food to them. So they would ignore it because it was not what they were trained to spot. In the same way, things like rabbits, deer, blowing bushes, grass swaying in the wind, none of that actually, is going to be detected, because those things are not what it's trained to see. So a lot of the things that used to create nuisance alarms actually are now just ignored. So that's a little quick primer on an AI. Now, there are some things, though, that come with this. As I've already mentioned, but by example, the more images you feed it, the more correct images, the more accurate the analytics become. So this created an immediate problem for us in 2014 because we realized that we needed a system that we could be continually updating and be learning from lots of different reference video. So what we did is let me boy, sorry, I'm off track here. Let me go back and say one more thing about anomaly detection, then I'll come back to the architecture. We also have a feature called Anomaly Detection. I just wanted to say in the industry, this has been a concept that's been discussed a lot, but I think a lot of times it's discussed incorrectly. Anomaly detection is not using AI the same way classifying a bicycle, a motorcycle, a bus would be. What anomaly detection does is it looks at a scene and it actually learns what is the normal pattern in that scene. And then if it sees something that's different, it will generate an alarm. So it's really more of a scene statistics tool. So in this case, this image, which is from a real event, there was a protest march in the spring of last year. And on the left, you can see it was not a very busy street. But then on the right, there was a march, a peaceful march, and the system was able to detect there are not normally people marching down the middle of the street at this time of day. And so it actually flagged that as an anomalous event. So anomaly is a little bit different than AI. It's really more of a statistics tool. And actually, maybe I'll show an example of this here in just a couple minutes. So let's see. All right, some misunderstandings about AI. So first, let me start with one of the ones that's kind of the one that comes up the most often, but is actually the most misleading and the trickiest to explain to customers. So customers will say to me, "So does your AI learn a camera over time to reduce false alarms?" Now, this is actually the question is flawed because AI doesn't work like that at all. In fact, AI learns from a collection of valid images, just like I used the human example before, to learn what is something that it wants to classify. It does not learn from an individual camera. In fact, it's already learned because the algorithm has gotten smarter by watching. It doesn't get smarter by watching the same camera. It gets smarter by learning from a compiled set of images across many cameras. So as soon as you turn that camera on, the algorithm has already learned what a person looks like. So if I just stretched my bad analogy one more step, I take my daughter who now has learned what a bowl of ice cream looks like, and I take her out to a new restaurant, and she's 2 years old. She doesn't need to learn anything from that restaurant. If she's sitting there munching on a French fry and the waiter walks by with a tray with a bowl of ice cream, she immediately drops the French fry and wants the ice cream. She didn't have to learn what the bowl of ice cream was at the restaurant. She already knew because she had been trained before what a bowl of ice cream looks like. And it's the same way with an AI algorithm. The algorithm is already trained. Now, a lot of this problem comes from, there have been analytics companies in the past. They were actually pretty good analytics companies in their day. They would have a feature where you could click on a false alarm and they say, well, we'll teach the system to ignore that false alarm. But they weren't actually at that point, reteaching the model. All they were doing is tweaking the parameters on what was basically a VCA algorithm. The way that AI works is it's already trained through positive images. So the problem was, how do you collect enough positive images to classify something? And then how do you update the model? Because one of the great benefits of AI is that you can keep adding new classes by just teaching it new examples. So what we did in 2016, when we launched our service, we actually launched it first, if you see here on the right side of our slide, as a cloud-based service. Now that had a bunch of benefits. First, it means we could push out new algorithm updates, even weekly if we wanted to. And at first, during those early years, we were making a lot of updates. We added, instead of just vehicles, we added bicycles and motorcycles and buses and trucks and just lots of different classes. We've been able to teach the system some custom classes for customers that had individual requirements. And anybody that was running our SaaS service immediately got all of those improved features because they were automatically pushed out to their edge devices. and everything was centrally managed. Very good architecture for this kind of a system. But just to be clear, we also have a lot of customers that do not want to use our cloud-based service, and so they build their own private system where they run the entire Anomaly on-prem in their facility, and in which case we give them model updates whenever they want to refresh. But this idea of sharing images and sharing models across cameras is one of the secret powers of these AI algorithms. Now, so we don't just spend the whole time killing people with PowerPoints, let's switch here for a second. And we're going to switch over to a live system. All right, so what you should see now is actually a Chrome browser. So one of the nice advantages of being with a cloud system is I also have a demo account. And let's see what's going on in my demo account now. So I'm going to log in. And my account is actually, we can see right now, I have cameras available to me all over the world. So for example, if I want to spy on my office, my boss, I can go to executive corridor right there in Rosh Hashanah, Israel, and I can see what's up, what's up. Well, I can see it's pretty late in the day there now. It's already almost 10 p.m. at night, so the lights are out. As you'd expect, everybody's gone home for the day. But let's look for something more interesting. Let's look at another camera. All right, so this is a live camera. This is closer to our time zone. Actually, if you're able to follow this, if the Zoom session is keeping up, those people right now are actually being tracked by our algorithm. And I can see here, even from just a centrally managed GUI, the rules that are set up. So one of my engineers set up a zone for people moving. There's those people again we were just talking about. All right. I have stopped vehicle. This is really in this causeway here, this this little dining area. Not too many stopped vehicles there. There's also grouping. Now here's a good example of how the AI works better, because we defined a grouping for 3 people in groups, but in this case we just turned on this entire scene. That means any movement in these trees, rain, anything like that doesn't bother the algorithm. We didn't have to mask out things. We didn't have to tweak, because the algorithm knows that a person is not these trees. It's just, it already doesn't have a problem with those false alarms. So let's go and take a look and see what's happening here on this camera. So I can see now, see what's going on. Oh, actually, here's a great example. So, I can, let's see. Well, here I can see last night, here's a moving in an area where this is actually, so this was middle of the night. In fact, this is a great example. You can see the ground is wet, so it's been raining. That vehicle is almost completely saturated from a camera standpoint because of lights and reflections. And not only are we able to detect it, but as you can see, I didn't have any problems around that with false alarms. So great detection. But also I see here another interesting thing. Looks like this morning at about 8:20, we did get an anomaly. Now, in this case, this isn't exactly like, bank heist kind of anomaly, but that, vehicles don't usually, this is a fairly lightly trafficked intersection, and vehicles don't stop in the morning in that spot. And so our system was able to notice that, there was a vehicle parked there along that roadway when normally there wouldn't be a vehicle there. So that's a great example of an anomaly where somebody would take a look at that and they'd say, oh, that's not a problem. We're not bothered at all by that. But just to illustrate that what we do in real time can also be done as an investigation, let me stick with the same camera. Let's say we were really interested in certain people that might have been going in and out of this building. So I'm going to do a quick investigation. Since I don't have a lot of time here, I'm just going to do this very quick. I'm going to jump over here and say, let's just look at the sidewalk area. I'm going to look for people moving. See, I'm going to get rid of some of these objects here, and instead I'm just going to look for people wearing red. All right. Now, time range, I'm going to go ahead and just look for the last 24 hours, because our system is fast enough, it really doesn't matter. I could do 48 hours, I could do 24 hours. It's still going to be pretty fast. Now, you can see right there, all right, I'm getting my first results in literally under 2 seconds. And at this pace, it looks like I'm going to probably be done in under 10 seconds. So in under 10 seconds, we were able to find all examples of people in red or wearing red on in the last 24 hours. Now, I want to point out in this illustration, we didn't have to reprocess the video. There was no time waiting for that. We didn't have to scroll through video to then figure out people in red. We were able to literally in 10 seconds look backwards 24 hours. I could have done this on 10 cameras and it would have actually been the same speed, because the secret to what we do is we're able to process that video very efficiently as it's received and create metadata on the fly. That gives us an extremely fast search capability. All right, so let's, since I've only got a little bit of time and I like demoing, but I'm going to break out of that because I did promise that we would talk about misconceptions. So let's go back to my PowerPoint here for a second. I mentioned this is our architecture. Let's go ahead here. So a second misunderstanding. Now this one, we're partially guilty on this because we used to always say thermal cameras help with analytics. And the reason is with the old VCA algorithms, oftentimes they did run much better on thermal cameras. But there's a reason for this. And this is why I took the time to explain the difference between VCA and AI. VCA likes the contrast that you get from thermal cameras because VCA was all about looking for motion and groups of pixels moving and then trying to infer from that, well, what do we think this group of pixels is? And so since thermal cameras give very high contrast, that helped those algorithms, a lot. Thermal cameras also did another thing. They would tend to wash out the nuisance objects like trees, brush, puddles, which would then eliminate false alarms. So in effect, yes, you got more contrast, but since a lot of the things that tended to be nuisance alarms tended to be cool, they were effectively washed out in the scene, so they were sort of ignored. I'd like to say that while that helped with VCA algorithms, that was sort of cheating, but it did help in a lot of situations. By the way, if you don't have artificial light, you need thermal cameras. So with the newer AI algorithms, they actually work better with color. And so with the color, even though they still work on thermal, the algorithms, first off, don't have the same problem with false alarms because they already know the difference between legitimate objects and nuisance objects. We already know that a person is not a tree. A vehicle is not a squirrel. Grass is not, a bicycle. So a lot of those nuisance alarms are already gone because AI algorithms just don't have a problem with a lot of those nuisance objects. But the other thing is the AI algorithms use a lot more of the pixels that are presented to it. So the algorithms use all of the pixels and all of the dynamic range as part of its math to classify the different objects that it's trying to detect. So the problem with the thermal camera now is pretty simple. Thermal cameras, at least as of today, don't have the same pixel density. And also by the very nature of the way thermal cameras work, their dynamic range is drastically reduced versus color cameras. So even though the AI algorithms can work with thermal cameras, you're not feeding it as much information, and therefore you're going to lose some of the distance detection, for example, some of the accuracy. So actually the AI algorithms prefer the color cameras whenever possible, even though they do work with thermal cameras. And I still find a lot of projects, including a very large project that we just did acceptance on, a month ago, where the consultant from several years back had specified a lot of thermal cameras, and we don't blame them for that. 3 years ago, that was the best practice they thought was being used for these outdoor cameras. But a lot of those cameras, it ended up we would have had maybe 2 to 3 times the detection distance with a color camera. So the AI algorithms really like color cameras. That's so that the old thermal camera fixes everything, not so much anymore. All right, the third misconception is that all AI needs GPUs. Now, the truth is AI algorithms are much, much more intensive than the old VCA, but they're still just software. GPUs 30 years ago were created to render video, to take, like if I say draw a red square on my screen, well, a GPU could take that command and draw a screen. It constructed video. That's what they were optimized to do. AI deep learning uses vector math to deconstruct video. Now, the reason I'm explaining this is that GPUs still have some of those advanced vector math instructions that help us deconstruct video. However, AI software benefits from hardware acceleration, but we really just need a few special vector instructions to run our algorithms efficiently. And now a lot of the newer Intel chips have those same instructions built in. So as a real practical example for our customers, even though we've done lots of GPU deployments, a more normal setup for us is if you're on a small site, let's say less than 10 cameras, we can take a simple low-cost box running an i5 processor and run up to 10 cameras on it. That's a very low-cost box, drop ship, plug and play, ready to go. And if you have a site with a lot of cameras, you can run our software on a Xeon processor. And now we've got, simple off-the-shelf drop ships, 19-inch one-use servers that can run 200 cameras without a GPU card. That's very high camera density. That's a super low cost per camera on the hardware. But also, since it's using standard generic Xeon processors, you can also right size it. If you only need 50 cameras, just buy a cheaper server to the size that you need. And these are all, as I say, can be literally overnight drop ship Dell or HP servers if you needed to. So it's a very efficient platform, and does not require the GPU cards that a lot of people think, both reducing cost, improving maintainability, all of those things. All right, so let's see. I think I only have time for maybe one question. So let's see if I got any zingers here. All right. Okay. So one of the questions, how if your system is spread out over a large geographic area, how does bandwidth affect your system? That actually is another one of the reasons I didn't get into it, but one of the big reasons we designed the system with federation built in. The way our system works, we have edge software. So if you took our edge software running on our little appliance on the top here or on your own Dell server at your local site, it converts that video frame by frame into metadata. At which point, depending on how many features you're using, you're going to need between 1 and 5 kilobits of bandwidth between our edge software and the core, either running in our cloud or running in your data center. That is like literally, we run this over 4G networks all the time. It runs very comfortably, even with standard data cards, standard data rates. It's very lightweight, and that's not by accident. That's because a lot of our big customers had geographically distributed systems. Okay. So I think with that, I apologize. I wish I had time for another question, but I'm actually on another session here starting in 2 minutes. They're probably like, "Where's AJ?" So thank you very much for today. If you have questions, please feel free to reach out to AgentVI at agentvi.com. We can help you with sizing of systems. We can help you with costing of systems. Or if you just have more questions about AI analytics and how they work and how to design with them more effectively, please feel free to reach out to us.